Hello and welcome to the next video. From today's video we'll start discussing about modern physics. So let's start with the basic experiments which initiated the era of modern physics, after doing which mankind came to know that the atoms can be further divided into subatomic particles, and electron was the first subatomic particle to be discovered. So let us study first the experiments which led to the discovery of electrons. So the discharge tube experiments were the first experiments which led to the discovery of electrons. In that we have a glass tube, and the glass tube is connected to the wires. Like there is two metal rods inside the glass tube, and they are connected to a negative charge and a positive charge. So a very high potential difference is applied between these electrodes. This is known as cathode, which is connected to the negative terminal, and the electrode which is connected to the positive terminal is known as anode. And what we do is, initially if it is at full atmospheric pressure, it requires very high voltage to produce the discharge or produce the sparks. Okay, so what we do is we withdraw the air or whatever is the material inside this. Let us assume for now it is an air, or say neon, which produces similar characteristics of color, which we'll discuss now, and it has air, and I start gradually sucking out the air, and I apply a very large potential difference across these electrodes. So what happens when the pressure drops to about 10 millimeter of mercury? We see a reddish glow. Okay, we see a reddish glow, which starts from the anode and go. It's not a very good diagram, and it glows almost till cathode. Okay, so this is we'll discuss what is the cause of these glows, but first let us discuss what we observe. So when the mercury is at 10 millimeter at 10 millimeter of Hg, we see a reddish glow right from anode almost up till cathode, and then when we continue pulling out air from this, what we see is this reddish glow contracts, and it now doesn't go all up till the cathode. It stops somewhere between, but near the cathode a bluish glow starts. And there is a gap between the bluish glow and the pinkish glow here, and the reddish glow here. Okay, and this dark space is known as Faraday's dark space. Okay, so this happens at about 3 to 4 mm of mercury. Okay, now when we further decrease the pressure of mercury from 3 to 4 mm to 1 mm, what happens is there is still a reddish glow here, not going right up to the cathode. There is a dark space, Faraday's dark space here, and the bluish glow, which was earlier here at 3 to 4 mercury, it shifts slightly towards the right. And now there is a dark space, small dark space, not as big dark space as the Faraday's dark space, but just little smaller dark space between this bluish glow and the cathode, and this is known as Crookes dark space. Crookes, the dark space between the bluish glow and the cathode is known as Crookes dark space. Okay, and finally, when we further decrease the mercury, the pressure of mercury from 1 mm to 0.01 mm, what we see is this reddish dark space which was there. Okay, they are separated into small bands. Okay, so the dark space, they are like bands now. Okay, so these bands are separated by small dark spaces, and this dark space is known as, this phenomenon is known as styration. Okay, so we have a dark space, we still have a between these reddish glows, and these are known as styrations. And from here we still have that old phenomenon where after this dark red glow we have some Faraday's dark space, and then we have cathode glow, which is bluish glow. And a little picture can be shown from Wikipedia I have taken. It shows the case, the middle case, where the pressure is about 3 to 4 mm, and we don't see much dark space here, but here we see a anode glow, the reddish glow, and the bluish glow, the cathode glow. Okay, so let us study the reason for this. Okay, so the reason why we see the glow. So now what happens here is, when I apply a very large potential difference, air will have already some quantity of ionized gas. They may be due to various reasons, maybe because of the cosmic rays which are coming from the universe, but in general any volume of air will at least have some small amount of ionic materials. So when I excuse me, so when I apply a very large potential difference between the anode and cathode, those ionized molecules starts getting accelerated. So if it is a positive ion, it starts getting accelerated to the positive side, and if it's electrons or negatively charged, if it is a positively charged, it starts getting attracted toward the cathode or the negative side, and if it's a negatively charged particle, it starts getting attracted towards the positive side. So in doing so, they face resistance from the air. Okay, they collide against the normal air molecules, and because of the high potential difference, they get high energy, and while collision they are able to produce more ions. Okay, they collide with the electrons, they are able to knock out those electrons and convert the molecules into positively charged ions and negative charged electrons. Okay, so negative charge electrons are small particles, they can easily find their way to the anode. Okay, but what happens to the positive charge ions? They are heavier particles, and they go with a great force and collide against the cathode metal. So when the positive charge ions, which are ionized because of the high potential difference, they go and hit the cathode, they further release lot of electrons. Okay, and now these electrons which are released are again getting attracted towards the anode, and while they are traveling towards the anode, okay, they further collide with the neutral charge, the neutral molecules, and they start to take the electrons out of their outer orbitals, or they start to ionize those neutral electrons. Okay, so when they start to neutral molecules, when they start to ionize these neutral molecules, energy is released, and this we see it as a faint bluish glow. Okay, so those ions, we have a very heavy density of positive ions here. Because those positive ions are continuously attracted towards this cathode, and so this region has a very heavy density of positive ions. Okay, and those ions, when they hit against this cathode, they release electrons, and those electrons, when they go and hit other neutral molecules, they ionize them, and because of them, that energy of ionization is seen as a bluish glow. So why do we see a dark space between the cathode and the bluish glow? We see the dark spaces because every electron has to travel some distance, okay, some average distance electrons have to travel before they get to collide with a molecule, neutral molecule. So for the average distance, they cannot, which the electron has to, because they are smaller particles, they can easily find way through the bigger molecular gaps. Okay, so the average, distance between to travel, because there is an average distance, so that's why there is a dark glow where they don't collide with any electron, so any molecule, so there is no ionization, and so there is no glow. Okay, so that is the reason for this dark space, the Crookes dark space, which is between the blue glow and the anode. What is the reason for the Faraday's dark space? Okay, the reason for the Faraday's dark space is when the electrons start colliding here, okay, they lose electrons, though they lose energy. Okay, after they travel here and they are colliding with the molecules and they are ionizing the molecules, in that process, because of these collisions, they lose energy. Excuse me. So so in this region they have lost energy, and while traveling to anode, they don't have sufficient energy to ionize the more molecules. So that is the reason they are accelerating at this phase, okay, and they lose their power to ionize the molecules, and that is the reason here we have a dark space here, dark region here. Okay, and this dark region is more than this dark region. Okay, it is of a bigger length. The reason being here, because there are very highly ionized, positively charged ions here. Here the electric force is higher. Moreover, it is nearer to the cathode, so the cathode is repelling the electrons at a very high speed here. So here electric field is much higher, stronger than this. So the acceleration of electrons in this region is much higher than in this region. So here electrons gain energy relatively more quickly, and they are able to ionize the ions here more sooner. But here the electric field is weaker, so they need to travel a larger distance to gain that energy, and that is the reason here the Faraday's dark space is larger than the Crookes dark space. And lastly, what is the reason for these dark patches? So the reason for these dark patches or striations are, now here again the electrons have gained energy, they ionize the ions, okay, by colliding with the neutral molecules, okay, and after collision they lose energy, so again there is a dark space here. Again they gain energy after traveling some distance, again there is a they collide with the neutral molecules and have sufficient energy to ionize them. So that's the reason there again you get a dark spot, a dark glow, and again after the collisions they again lose their energy. So the process goes so on and so forth, and that is the reason we have an alternating band of dark, bright spot and dark spots. So this is the basic overview of the cathode ray experiment, and let us study the properties of some of the properties of cathode ray experiment. First property is cathode ray are emitted normally to the cathode, or the electrons are released normally to the cathode. So if I have this type of shape, a spherical shape, the cathode ray will be emitted somewhat like this, normally to the spherical. Second property is they travel in straight lines. So if I put a fan or something, an object in the path of the cathode ray, because they travel in straight line like light, so they cast shadows of the object like light cast the shadows. So cathode rays travel in a straight line, and also they have some mass, they have some mechanical force, they exert a mechanical force. So if I place this fan in a proper angle, so you will see that the cathode ray are able to move the fan or rotate the fan. Excuse me. So these are some of the basic properties of cathode rays. But one question still remains unanswered, and the question is, how do we know that these are actually electrons, these are actually caused by electrons which are negatively charged particles? How do we know that these are negative charge and not positive charge, or neutral charge, or some other phenomenon is not going on? So the answer to this was given by J.J. Thomson. Okay, the answer to this was given by J.J. Thomson, and because of that, J.J. Thomson is credited with the discovery of electrons. Okay, and the experiment, this is on again Wikipedia, the experimental setup which helped us to determine that these are actually negative charged particles and they travel from cathode to anode, because obviously negatively charged particles will travel from cathode to anode. This was proved by J.J. Thomson, and experimental setup is shown here. Okay, so we have a cathode, and the figure is slightly smaller. So okay, let me go here. So we have a cathode and we have an anode. So anode has a hole inside it. If you see, if you zoom it, this is the anode, and anode will have the hole inside it. So what will happen is the electrons, if at our assumption that electrons are traveling, so the negatively charged particles which are traveling from cathode to anode will pass straight through the holes. Okay, and then you will see a glow here. Okay, you will see a glow in this end of the glass when those negatively charged ions or particles or electrons hit against this wall, end of this wall. You will see that because of the ionization or whatever phenomenon, this end you will see a glow. So that proves that the particles which are actually traveling are electrons. They are negatively charged particles, and they which travel right through they are traveling from cathode right through the anode and traveling towards this. So now J.J. Thomson not only stopped at here, he also determined what is the property of these electrons, what is the fundamental property. So the fundamental property which he discovered was the E by M ratio of those particles. Those particles were electrons, and when he determined the E by M ratio of these particles, he used the E by M ratio. He filled air, he filled neon, he filled carbon dioxide, he filled various types of gases inside this. Okay, and though he filled different types of gases, different type of materials inside this, still he found a basic fundamental quantity of the particles which are hitting this, which is the E by M. For all those different materials, this E by M ratio remained same. So that's the reason why we concluded, or he concluded, that we have stumbled upon a basic particle which is there in all material. Okay, so all material can be further divided into smaller particles, and one of the smaller particles is same for every type of material, and that particle has a basic property. I can identify that particle through this basic property of E by M ratio. So how did he find out this E by M ratio for that particle? So he did this type of setup. First, we put a plate between in this position like this. Okay, and we connect it to charges. So suppose I am connecting it to plus, and here I am connecting it to minus. Okay, and if I switch on this electric field, what will happen? This field will, the electrons which is coming from here will get diverted, because they will be accelerated by this field. So this positive will attract those electrons, so that's why the electrons will get deviated. Okay. and another trick he did was, he applied, I know that if I apply a magnetic field to a moving body, moving charge, we studied from magnetism that if we apply a magnetic field on a moving charge, the magnetic field will exert a force on the moving charge. Okay, so that's why he also, to apply a force on this moving body, he also applied a magnetic field on this. Okay, so this is the representation of magnetic field, or you can also represent the magnetic field in some books like this. Okay, some books the magnetic field is represented. Magnetic field is applied where we are applying an electric field, and we can apply this magnetic field in such a way that the direction of magnetic field is opposite to the direction of these electric fields. So I can apply the magnetic field in such a way so as to neutralize the effect of electric field here applied by this plate. So if you look at this one, it's a very good illustration. You see that this electric field is switched on and off, and that is diverting these electrons, and I can apply a magnetic field in such a manner that the electric field is neutralized by the magnetic field. The magnetic field is equal, magnetic force will be equal and opposite to the electric force. Okay, so let us see how we can do that. So we know that magnetic force on any charged particle in motion is QVB. Correct? So QVB is the magnetic force, and it is equal and opposite to the electric force. So instead of writing Q, let me write actual notation of charge of an electron, which is EVB, which is the magnetic force on the electron, that is equal to the electric force, which is equal to E times E. Okay, electric force due to an electric field will be given by the charge multiplied by the electric field. So here E gets cancelled, and I get V is equal to E by B. Correct? So now we have got a relationship between velocity, the velocity at E by B. Now one thing to note here is, let me try to find what is the value of V. To find the value of V, which is coming out here, I will use the formula of kinetic energy. So let me define the potential difference between the cathode and anode as capital V. Okay, note, capital V is not the potential difference between this and this. Capital V is the potential difference between the cathode and anode. I have defined the potential difference between this plate and this plate as V dash. Okay, so when an electron leaves from here to here, it is attracted by the electric field. So the work done by the electric field is, we know that it is equal to E into V. Okay, the potential is the work done per unit charge. So the total work done on this on the electron will be equal to the charge into potential, and the total work done on this electron, which is EV, is converted into the kinetic energy of the electron. So the kinetic energy of the electron will be equal to half mv squared. So from this we will get half mv. If I substitute the value of v from here to here, I will get E by B whole squared is equal to E into V. So what will be E by M then? E by M will be obtained by half, taking this V to the denominator here, half V E by B whole squared. Notice one difference. This V, this potential is the potential across this cathode and anode. Okay. This E is the electric field, not the electric field between the cathode and anode. This E is the electric field between these two plates. So if I want to write E in terms of V, it will be V dash. Suppose the separation is D here, E will be equal to V dash by D and not V by D, because the electric field which is considered here is this electric field, because this is the electric field which will try to deflect the electron. Okay, so the electric field which balances the magnetic field is this electric field, and the potential V here is, so electric field is the electric field here, potential V is the potential V between these 2 points. So using this, Thomson determined the value of E by M, which is the fundamental property of any electron. E is fundamental, M is fundamental. He determined the ratio E by M, but still we don't know what is the individual value of the electric field E. So how do we find the value of E? So E was found by Millikan. Okay, so Millikan famous oil drop experiment is what was used to find the value of E, and because of that Millikan won the Nobel Prize. So let us find out how Millikan found out the value of E of a electron. So he found out by Millikan's famous oil drop experiment. So what Millikan did was he used this type of setup, which is there is a container here in which he is spraying oil droplets from here. The bottom of the container has porous plate, and below that there is another plate. Okay, these are very close to each other and almost parallel to each other, closely maintained parallel to each other, and he is observing this through a microscope. Okay, and he is applying an electric field across this plate. Okay, so this is the direction of the electric field applied, which can be applied by attaching a battery, and this electric field can be tightly controlled. So when he sprays the oil drops, these oil drops fall through this air, and because of friction from air, these oil drops get charged. Okay, we know that if you rub like glass rod or oil drops, they attain some charges because of the friction. Friction will knock out some of the electrons and they will become charged. So now these charged droplets are falling through this plate, and I can control the electric field in this region. E can be controlled so that the oil drop remains stationary and does not fall down after this. So how can we do that? Let us study the forces on this. So I have applied an electric field E, which is opposing the gravitational force. Okay, so E will be in this direction, and the the magnitude of the electric force will be EQ in the top direction. Magnetic force will be mg, the gravitational force will be mg. And also, if any oil drops or any drops are falling through a medium like air, it will also experience a force of buoyancy, and we know that force of buoyancy will be opposite to the direction of gravity, and EQ will be equal to, so if we balance this, okay, balance this is EQ. If we balance the forces, if there is no net force acting on this, we can get this equation: EQ will be equal to mg minus b. The magnetic force will be the electric force will be equal to the net force of magnetic and buoyancy force. And we know that the gravitational force mg, the weight of this can be written as the volume is 4 by 3 pi r cube of the oil drop, volume into the density of the oil drop, which I will write it as rho. So mass is density times volume into g. So g is still there. And buoyancy, what is the buoyancy? Buoyancy is equal to the weight. If you remember from 11 discussion, buoyancy will be equal to the weight of the displaced air. Okay. So what is the weight of the displaced air? Weight of the displaced air will be the mass of displaced air. Mass of the displaced air is 4 by the volume, 4 by 3 pi r cube is the volume of displaced air, into the density of displaced air, which is sigma. Sigma, I am writing the density of space air is sigma. So volume into density is the mass of the displaced air times g. So from this equation, if we solve, we will get, doing some basic algebra, 4 by 3 pi r cube is common, g is common, rho minus g divided by E comes at the denominator as E. So I have found out Q. What is the Q of this oil drop? So Q of this oil drop is this expression. Now I know 4, I know pi, I know radius. I don't know radius yet. I'll find out the radius. Into density of the oil, we know density of oil, we know, this is sigma, not g. This will be sigma. I know the density of air, and I can control the electric field. I will know how much electric field I have applied. The only variable now left is rho. Okay. Excuse me. So how do I r, the only variable left is r. So how can I found the value of r? So the value of r can be found out using the concept of terminal velocity. Okay. So to find the value of r, what I will do is, I will now switch off this electric field. Okay, now it is, electric field is switched on, the oil drop is perfectly balanced. Now if I switch off the electric field, the net force faced by this oil drop in downward direction will be equal to mg minus b. Correct? So now E is switched off, so the net force in downward direction is mg minus b. So what will be resisting this mg minus b? The force which will be resisting this mg minus b will be the viscous force. Okay, so because of the viscosity of the air will resist the net force in the downward direction while the droplet is falling. Viscous force will act in opposite direction. Okay, and we know that the viscous force will be equal to, from our, if you remember again the definition of viscous force from your class 11th or high secondary school on viscosity, classes on viscosity, it would be 6 pi eta r into velocity. Okay, the terminal velocity or the velocity through which this drop is falling. Eta is the property, viscosity property. Okay, so this is a constant depending on the medium in which that drop is falling. So if again, what will be mg minus b? Mg minus b will be again this term, 4 by 3 pi r cube g rho minus sigma. Now instead of it being eq, it will be just this term, 6 pi eta rv, and using this expression I can find the value of r as r. If I just do some simple algebra, r will be equal to this, r will get cancelled to this r squared, so obviously r will be some square, because it is r squared, some square root term. If you just do this simple algebra, you will get r will be equal to 9 eta v divided by 2 rho minus sigma into g. Okay, so if I know the value of v, I can easily find the value of r, and I can measure the value of v, the velocity through which it is falling, by calibrating it, by noting the time through which it falls, some fixed distance. I can measure it through this my microscope from here, or telescope, not telescope, microscope, because it is very small. I can, using this microscope, I can measure what is the time the drop takes to fall through particular distances, and I can measure the value of v. So I know all the data now. So if I just substitute the value of r from this equation to this equation, I will get q is equal to, I will just again write the final expression. This is simple algebra which you can do as an exercise in your free time. I recommend you practice doing that algebra, so that your concepts are clear. Divided by 2 rho minus sigma g. So now this is the final expression for q. I know E, I can control E, I can measure E by knowing what is the battery potential difference I have applied. Eta is the property of the viscous property of the material, of the fluid. Excuse me. Velocity I have measured, and rho and sigma are the densities of oil and air respectively, and g is the gravitational constant. So using this, Millikan found out what is the value of q, and once he found out what is the value of q, okay, he noted, their team did lots and lots of experiments, thousands of experiments, and what they found out is the q which was coming in this answer, they varied the material, they varied rho, they varied the electric field, they varied lot of parameters, and found out every time the value of q which they were getting was a multiple of 1.6 into 10 to the power minus 19 coulomb. Every time they were doing that experiment, they found that E was a multiple of this quantity, and we know that charge is quantized. Okay, so from this they deduced that the charge on that fundamental particle, the minimum entity, the fundamental particle, should be 1.6 into 10 to the power minus 19 coulomb. So that's how they found out what is the charge of an electron. Now this completes our discussion of the first part of modern physics, which is how electrons were discovered using electric current through gases and various experiments to determine the fundamental quantities of E by M and E. In the next video we will study what revolutionized modern physics, basically the photoelectric effect, which concluded that light behaves as wave as well as particle also. And in the next video we will discuss about the photoelectric effect.